Dear colleagues, the task of this presentation is to introduce a method for the calculation of the flow rate in a ductwork. This method allows to assess the air delivered by each terminal and the corresponding pressure drops, both across every branch and the overall one, so that we can choose the capacity of the fan. The good news is it can be applied at every network, either supply or return duct, regardless with its complexity. Let's see together how. The problem we must solve is the following. Given is the duct geometry, the data of the air terminals, and the total flow. We need to find the flow at every user, the delta P across the fan, and across every branch. We assume to have only one fan per network, but of course there can be many networks, for example, supply, return, exhaust, and intake. There are possible two applications. Either a network is existing and the fan must be chosen to get a wanted flow, or a network must be sized to comply a flow rate demand with a given delta P. Let's see now how to proceed. First, we need to identify one network, for example, supply, and define the air density, the fan flow rate, and the duct's material in order to know the roughness. Per each branch, it must be given the size of the channel, the length of the channel, the fittings, can be T's, elbows, reductions, etc., the valves, and the terminals with their characteristic. Then we need to calculate the hydraulic resistance RT of each terminal by using this formula, where the delta P is the delta pressure across the terminal at a nominal flow Q. Now we calculate the hydraulic resistance of the duct up to the terminal using this formula, where ρ is the air density, capital A is the cross-sectional area, capital D the hydraulic diameter, capital L the equivalent length of the duct, and F the friction factor, as displayed in the legend. The hydraulic diameter, capital D, for a circular duct is just the diameter of the pipe. For a rectangular duct is given by this formula, where A and B are the sizes of the channel. The equivalent length of the channel, capital L, is the sum of the geometric length of the duct plus an additional length that takes into consideration the fittings. The table below is just an example for circular ducts. For a smooth elbow, having the ratio R over D equals to 1, we need to consider an additional length of 15 times the diameter. The friction factor, F, is calculated with the formula below, where E is the pipe roughness and must be expressed in the same unit as the diameter. The friction factor is dimensionless. We sum the resistance above with the resistance of the terminal. They are in sequence, and we obtain the resistance of the branch RB. We repeat for the remaining branches having a common node. Then we make the parallel, where K is the hydraulic conductance. The parallel of the conductance is the sum of the conductance of the corresponding branches, and the conductance is defined as the inverse of the square root of the resistance. We calculate the resistance of the tree, R3, considering the parallel above, this one, plus the series of the duct upstream, RD. For the series, we sum the resistances. Also, RD plus R parallel above calculated, where RD is the resistance of the duct upstream. This is the resistance of the new tree, taking into consideration also the distribution duct. We calculate the resistance of the remaining branches having the same node in common. Then we calculate the new parallel among them and the tree already found, plus the series of the upstream duct. We get the resistance of another tree, R3 prime, RD prime, plus R parallel prime, where the conductance of the parallel prime is the sum of the conductance of the tree already calculated above, plus the conductance of the two new branches having the same node in common. Repeat the procedure till to the main duct downstream the fan. At this point, we have calculated the resistance of the whole network, from the fan up to the terminals. We calculate the delta P across the fan with this formula, R of the network times flow rate square, where the flow rate Q fan must be known. From now on, we can calculate the flow of each branch of the system and the pressure at each node. The flow of the first tree downstream the fan is Q of the fan times the ratio between the conductance of the tree and the sum of the conductance of the tree plus the one of the branches with the same node. We assess the relative pressure of the node N1 downstream the fan by means of this formula. R1 times Q fan square, where R1 is the resistance of the duct between the fan and the first node. The pressure of the node is the difference between the delta P of the fan and the delta P calculated aside. The flow of the generic branch N is calculated by replacing Q fan with Q of the tree with their own conductance. The conductance is referring to the tree for which we need to calculate the flow rate. In the same way, we calculate the pressure at the following generic node N. Delta Pn equals Rn times Q3 square, where Rn is the resistance of the duct between the node N-1 and the node N. And the pressure is the delta P above minus the current delta P. We want to run now an example with some real numbers. Given are the air density, the pipe material, therefore the roughness, then the geometry of the network, that means for every branch is known the length and the size of the duct, and moreover are known the terminals data. We have three types, T1, T2 and T3, and for each of them we know the flow rate in cubic meter per hour and the nominal delta P. From them we can calculate the hydraulic resistance, that is the ratio between the delta P and the nominal flow square. Moreover, we know the flow of the fan, 8,500 cubic meter per hour. The resistance of the duct containing the terminal are given by the formula seen already. For the terminal N1, the roughness E is 0.15. This roughness we keep constant for the complete network. The corresponding diameter of the terminal is 250 mm, and we can calculate the cross-section A. The calculation gives for the friction factor the value of 0.017 and the corresponding hydraulic resistance Rd turns into 341 kg over meter to the 7th power. This is a unit of the hydraulic resistance. Now we calculate the resistance of the complete branch by adding the terminals 1. Therefore, we add 114 to the value calculated above, and we get 455. And we repeat it for all 5 terminals of the network. Then we calculate the resistance of the distribution duct Rd between each node A, B, and C. and we calculate the resistance of the tree at the farthest terminals, that is the parallel among the branch N4 and N5 in series with the duct BC. The parallel we achieve by adding the corresponding conductance 0.044 and transforming the conductance into resistance by making the inverse of the square root, we get this number. The resistance of the sequence between the parallel and the duct is the sum of the resistances that turns into 561. Once we calculate the resistance of the tree R3, we step to the next tree R3 prime by doing the parallel between the old tree and the branches N2 and N3. We are now running the parallel of 3 branches and we make the sum of the corresponding conductance, and this is the resistance. Finally, we make the resistance of the series between the parallel already found and the one of the duct upstream. We come to 98. We repeat the procedure for the last 3, that is R3 second, by means of the parallel among 3' and the branch N1 in series with the fan duct 0A. The parallel among the 3' and the branch B1 is achieved by adding the corresponding conductances. From the conductance of the parallel, we get the resistance, and then we add the resistance of the parallel with the resistance of the duct upstream, getting 55. That is the resistance of the complete network. When we have this resistance, we can calculate the pressure drop of the fan needed to supply the network. That is the product between that resistance and the flow of the fan square. We find 304 Pascal. The delta P along the duct 0A, the first duct supplied by the fan, is the product between the resistance of the duct that we have calculated, it is equal to 9, times the flow rate of the fan square. It turns into 49 Pascal. The pressure at the node A is the difference between the delta P of the fan and the delta P of the duct. We have 255 Pascal. Now we need to find the flows of all the branches of the network, and for doing that we used the formula displayed on the left column of the table, this column. The value is displayed on the right side. We have done for every terminal and also for the duct branches AB and BC. The values are also displayed in the flowchart at the corresponding positions. Now we can get the delta pressure at every branch thanks to the flow rate calculated in the previous slide. The delta pressure is given by the same formula applied for the different branches, and from the delta P we can also calculate the pressure at the internal nodes. At the node A we have already calculated, we made for the node B and for the node C. Why we need this information? Because we can assess the correctness of our procedure subtracting the pressure drop across each branch to the pressure of the node. And if you are correct, we should find 0 at the end of each terminal. Actually, they are matching. This value is matching, and this value is also matching. I hope you have enjoyed my presentation. Please let me know your comments, and thanks for your attendance. See you next time. Bye bye.